you will observe what we will get. So I calculate the derivative of this diffusion flux step by step, and I get a formula like this, and I can observe that this is nothing more like special transposition of the initial equilibrium distribution function. And therefore, I can express it in the following manner. So here's the equilibrium, and here's the normal of the interface between the phases. And finally, I can obtain the following equations. So here's the basic one. This is just the advection-diffusion equation, which we can interpret as a equation for the temperature tracking or some other passive scalar field. And in case of the multiphase flows, we have to add the special term which will account for the anti-diffusion. And thanks to it, we will be able to calculate the behavior of the multiphase flow. And now we are very happy because we can use the algorithm which you have already seen to solve these equations. And we call it the double distribution function approach. And this means that we will just assign another distribution function which will be responsible for recovering this passive scalar field. So here you've got the same algorithm, just revisited. And instead of f letter, we'll use a different letter. This will be a different variable in the code. And it will account for the distribution of this passive scalar field. And the coupling is given in terms of the velocity. So here we plug in the velocity of the external flow solved in the hydrodynamic sphere by these F distributions. Good. Now we have some sample results. First of all is the basic one. It's the temperature field. So this is just the advection-diffusion equation. And here we have an example of a von Karman state. So this is a flow around a hot cylinder. So to validate the code, we have run a huge amount of numerical experiments. They are given in the table. They are given in the table here. So what is important here that we use the different set of the lattices. We call them small, medium, and large. The largest one here is about 7 million of cells, so it takes a while to compute it, even on a supercomputing cluster. And the results are given as follows. So here we have once again the case. So this is the how big was the mesh and how difficult was it in terms of the numerical values for the relaxation parameters. So the higher the prompt number, whatever it is not important at the moment. The higher it is, the more difficult is the problem in terms of numerics for the solver. On these columns, we see different kernels which have been tested. And finally, the last column represents the reference result. So these are the values which we shall have obtained. But we can see that when, let's say, the numerical diffusivity is quite good, the solvers in each of the cases will give us a valuable result. But once we go to some unfavorable regime, then we will suffer from the numerical problems with it. And the mesh would need to be really, really large to give us valuable results. And the key point to take from this slide is to remember that the size of the mesh was like this. So this was about 7 million cells in the most difficult case. And later on, you will see how much memory and computational time is needed to solve such a case, and what can we do to elevate it. And now I will pass the screen to MICHAԼ, which will tell you more about the multiphase flows and the structure of the solver. Okay, MICHAЛ, please, now is your turn.
Okay, so now a little bit about our applications for the multiphase flow. It came from oil and gas industries, and there's a problem of hydraulic fracturing, and one step of this geoengineering process is that you basically using high pressure, you induce cracks in underground rock, and then for those cracks to stay open and provide flow paths for gas or oil, you try to put some support in them. So that's basically grains of various materials that are transferred by the fluid inside the rock fracture structure. And then when you release the pressure, because you need to, you would like the pressure to go back to sort of hydrostatic, so the gas or oil could come out to the surface. Then these grains get squeezed by the overburden pressure, and they are more or less flat. So this pure slide is the conceptual model behind the geometry. We started with Geological Institute in Poland, and we started with some experimental setup, which I will try to show. That's the link that's for everyone, but that also should work here. Okay, so that's not numerical analysis. That's experimental setup. So the basic problem is how the multiphase front will propagate in such domains. So this is the almost two-dimensional domain. We have glass plates. Between there are obstacles that are in shape of cylinders. We have two fluids. In this case, it's water and mineral oil. And the less viscous fluid invades the space occupied by the more viscous fluid. There is a surface tension. And the result of the simulation is the shape of the front and the final saturation. So how much of the invading or defending fluid stays in the domain after the front reaches the steady state. Okay, so going back to slides. So the numerical results of the numerical simulations could be summarized in still frame in something like that. So the color represents time. Time to occupy the part of the domain. So it's sort of age of the position of the front. So the blue ones represents the least advanced part. The white ones is the oldest front. This case represents the case when the invading where there's high capillary interaction, so the shape of the front is strongly capillary dominated, and the front is transferred not in continuous way, but in a series of jumps that are often quite rapid and linear. So this is like going from one stable configuration to another. This is not very desired situation, and there is a high pressure to overcome if you want to put your front for a next step. And here is similar configuration. So the obstacles lay in the same positions, but the invading fluid is much less viscous and with much less influence of the capillary number. So it's similar to the situation you would add surfactant to the invading fluid. So you will get different shape of the front. So using our numerical tools, you could try to determine the post breakthrough configuration of the system, the amount of pressure you need or amount of work is needed in certain configurations, and to build the upscaled model that could be used to determine properties of the whole rock reservoir. You could say that it's way easier probably to make experiments, but it's problematic to extract field information from experiments. For example, pressure distribution, which is the second row, or the velocity distribution inside the domain. So you will get the area which is occupied by fluid A or fluid B, but the additional information that could be useful to extract some more information about how the front propagates and what could we do to obtain more desired effect. That information is hard to obtain in experiments, especially as this is very sensitive system or close to chaotic. Then there is the question how to which extent you could not see you influence the experiments by the way you measure it. Okay, so going back to numerics, our solver is written almost completely in CUDA, with one single big exception, that the code is generated using the self-made template tool. So that each physical model is described in some generic terms like the number of directions, so basically the stencil, the number of additional parameters, the number of integrals that must be calculated along all the domain, and some model the dynamics, so the collision model itself described in symbolic algebra, and all those data plus some generic code that works for every model is combined using the template tool to obtain the model itself, and the model tuned code, which could be then compiled using an VCC. We make that additional step because there's a lot of stencil access patterns that are model dependent, and using template tools we could optimize the memory access for each model individually, which makes them way faster, especially when we use optimization for number of algebraic expressions, especially in the index access part of the code. And I told you already that there's a huge significant memory constraint for this system. So while in most CFD we try to use different size meshes or higher order schemes, in Lattice Boltzmann you are limited to second order schemes, so you need to go for high resolution meshes. And for cases Grzesiek showed you, there's those are memory requirements, so it's almost 1 kilobyte per single node in 3 dimensionals, which is not big, but we need quite a lot of those to obtain realistic simulations, especially if you want to see turbulence or those types of phenomena. So for single cube in 3 dimensions that have 1,000 nodes in each direction, this is not very big. This is almost terabyte of memory. If you would like to simulate cars or planes, then that would be 2 or 3 orders of magnitude bigger. So Lattice Boltzmann is rather confined to phenomena that could fit in thousands, so maybe 2,000. To elevate that, we could use the techniques that are typical for older CFD methods. So mesh refinement or overlapping mesh, this is work in progress in our solver. We would like to fully develop the overlapping mesh technique, but we are still not there yet. Okay, I think that's why are you using adjoint? Okay, so I think that's all for me. That's templated CUDA for at GitHub. All the code is available, and I think that's time for questions. Okay, why are you using adjoint model?
Hello. Do you have any questions?
I've seen at least one. Why are you using adjoint model? Our solver is capable of optimization, so that's the adjoint part. So we could generate the direct code and the adjoint part. This is discrete adjoint, and to use it directly for optimization. For example, the drag optimization or heat transfer optimization that could be done. So the adjoint is like sort of extra to the code. It's not part of the numerical optimization.
Okay.
Is the solver 100 free? Yes, solver is open source GPL license, I think.
Okay, we have to finish with this. I encourage those who are interested in this method and using it, please contact with the authors.